Hi guys, I hope you guys are doing great. Welcome to week 7 of operating system course. We are going to study today about deadlocks. It's a very important concept in operating systems. So before going there, as always, I just want to discuss about some things we have done up till now. So we have discussed about several concepts that are related to processes and threads, and today is the last week and the last lectures that is going to talk about processes, and after that we are going to dive into memory and some other stuff as well. So up till now, which is almost halfway around of this course, we have studied a lot about processes, and you can understand why we have been doing that, because everything is related to the processor and how to manage processor wisely, how to manage the time of a processor wisely. Operating system has to do a lot of things, and we have talked about a lot of scheduling algorithms. We have talked about different synchronization techniques. We have talked about how to split processes into threads, how to synchronize threads. We have done an assignment on threads as well. So we have done a lot of things that are related to processes, and next important thing after the processor is the main memory. So we are going to talk about main memory from next week onwards, and then few other things that are related to file system and security and protection and so on. So we're going to talk about that in coming weeks. But today's topic is extremely important. I'm also planning at least one question from this topic in your final exam, so make sure you understand this topic very carefully. It's an interesting topic. There are a couple of exercises that we're going to do, not necessarily programming exercises. There are some other exercises that you can do using pen and paper, and definitely there is going to be a practical exercise in the form of programming exercise, which I'm going to do it for you, and you can practice that with different inputs and so on. So we're going to look at that as well. Now, before I dive into the lecture, a couple of other things I want to discuss. First thing is assignment number 1. You will be seeing your marks on Blackboard very soon. Hopefully, by the time this lecture is uploaded, you will see your marks for the assignment. And I'm extremely happy to see your progress, to see your performance in assignment number 1. Almost everybody has done really good. That makes me very happy to see that you guys are understanding the concepts. Now the assignment was I won't say that it was too difficult, but I won't say it was easy as well, because there were so many things that you had to learn on your own. And I can see a lot of students approaching me, discussing about their progress, how they are doing, what do they think about it. So I really like this approach. I'm sure the other students who have not approached me, it's not necessary to approach me always. You can always go to internet and look at information available on the internet as well, and I'm sure you guys have done that, because I can see that in the reasoning that you have provided for requirement number 3 in the assignment. So I can see that, and that makes me very happy that everybody is understanding the concept, and you guys can see the exceptions where threads can work, where threads cannot work. I mean, they can always work, but it depends upon the performance of your system, and based on that performance, sometimes threads can be very fast. Sometimes threads can add an overhead to your system, and that most of you have seen. Some of the students, they had threads running faster than the other program. Some students had other program running faster than the threads. It's absolutely fine. It was an open question, so not necessarily for everybody threads had to run faster, or the other program without threads had to run faster. So it's absolutely fine what you have done, as long as you have given valid reasons. Most of you have given valid reasons, and that are making a lot of sense to me. So most of you have got good marks, and since it was our first assessment, I'm open to discuss. If you think the marks uploaded for you are not making sense, you think you deserve more than what you got, please come back to me and we can discuss. I can provide you your assessments. You can have a look at them, and we can always discuss that, right? So please do that, and obviously if you got full marks, you should be happy. But if you lost marks somewhere, and you think you have done better than what you got, please always come back to me and we can discuss that. So this is this, and this week we are going to have another assignment number 2, and I'm going to talk about that assignment at the end of this lecture. So make sure you go through this lecture, and maybe I'm going to discuss that at the end of our lab exercise as well. I have no idea how I'm going to plan this, but let's see how it's going to end up. But you're going to find some information for your assignment number 2 in this lecture, either at the end of the theoretical part or at the end of the lab exercise. So don't miss that. I'm going to upload obviously the Word file for you like I did last time, and you have to solve it within that Word file. As for the assignments, please make sure that you submit everything inside the Word file. Don't give me zip files, because there are separate files, and sometimes students do have problem uploading that file. Sometimes I have problem downloading those files. Some of those files run for me, some of those don't run for me. I've actually dropped an email to few of the students where I was not able to open their assignments. Even the PDF files, I was not able to open them. So please make sure you do everything inside the Word file. Don't convert it into PDF. You can upload the Word file as it is to me, and I can download and put your marks in that. So please, for the coming assignment, do everything within the Word file. Don't create separate files. Don't put screenshots as pictures inside the zip file. Put screenshots inside the Word file. Most of you have done this, which is good. Some of the students, they have added the screenshots separately. Some of them, they have just created a PDF. Some of them, they have just done a zip file. So let's keep it simple. Let's put everything inside the Word file. That makes my life easier. That would make your life easier as well. So please do that for assignment number 2, and then we are going to have a project. I want to give you project maybe next week, so that you have enough time to complete that. I don't want to give you project in week 10 and then it will be a mess for you. I'm sure other courses are going to give you projects as well. So because of this pandemic, I mean, we had to change the assessments. So I want to give you the project a little bit early, so that you have at least 4-5 weeks to complete that project, and then we can always have the presentation and revision at the end of this course. So I'm gonna jump to the lecture now, and as always, I'm gonna create separate 2 videos, and again, there are several reasons for doing that. One of the reasons is uploading. It takes a lot of time. I have been told by our Center of Learning and Center of Learning that there is a lot of backlog in uploading files to capture media to Blackboard. So a lot of files I upload, normally they keep on processing. I have uploaded the last lecture for operating system I think on Monday, and it up till Wednesday it was not working. It was still processing, so I had to upload on YouTube and then had to provide you the link for YouTube. So sometimes it does happen, because a lot of online processing is happening, because if processing is not done properly, you might not be able to see the code I am writing. This is what happened in our first lecture, right? So processing takes a lot of time. It depends upon the size of your video as well. So that's why I normally create 2 videos, just to split them, so that it makes my life easier uploading them and processing them. So let's get back, let's get started with our topic. So it's called deadlock. What is a deadlock? Well, deadlock is a concept in operating system in which a process is looking for a resource. For example, a process P1 is looking for scanner S1, and there is a process P2 that is looking for printer, for example, maybe printer. Now in order for P1 to complete its execution, it needs to get scanner and it needs to get printer as well. Similarly, for process 2 to complete its execution, process 2 needs printer and scanner. This is how the code for these processes are written, right? Now process 1 has scanner. So process 1 has already been given scanner, or let's say process 1 is looking for a scanner, and it has the processor. I don't want to confuse you guys, since it's done this way that process 1 is having a scanner. So let's say that. So process 1 is already assigned a scanner S1, and process 2 is assigned a printer, right? So process 1 is right now using scanner, and process 2 is now using printer. So process 2 is printing some pages, process 1 is printing some is scanning some pages as well. Now in order for process 1 to complete, after process 1 is done scanning, it needs printer as well, right? Similarly, after P2 is done printing, it needs a scanner as well to complete. Now what is happening right now is, if P1 looks for printer, printer is already assigned to P2. So process 1 cannot get a printer because printer is assigned to P2. Similarly, if process 2 looks for a scanner cannot be given to process 2 because it has already been given to S1, so it cannot complete. So both of them are stuck. They keep on processing, but they will not complete, since one of the resource that is assigned to another process is required by process 1. Similarly, the resource that is being required by P2 is assigned to P1, and they cannot complete. I'm going to give you some more examples of this, so don't worry if you don't understand right now, because I was trying to get simple words for you to make you understand, but when you see pictures coming up, you will understand what is going on. So in simple words, a process is looking for a resource. That resource has already been assigned to another process. So process 1 cannot complete its execution because the resource it's looking for has already been assigned to another process, and that other process is looking for a resource to complete its execution, which has been assigned to the process which is looking for the resource that is being used by process 2. So they are stuck in a loop, they are stuck in a deadlock, and they both cannot finish their execution, their completion. Now I'm going to explain a little bit more, and you will see some diagrams and you will understand in more detail what a deadlock is. I don't want to further confuse you by getting stuck to this diagram. So let's talk further, and we will get back to our this example once again. Now when we are drawing deadlocks, when we are trying to explain deadlocks, normally the processes, they are drawn in circles, like what I did over here. So if I'm drawing a process, I will draw a circle and write the process name inside, right? Similarly, for resources, resources are normally drawn in squares. So if I have something like this, it means it's a resource. It's a resource like this. So you will see something like this. So what is happening over here is, this is a resource because it's in a square, and this is a process since it's in circles. Similarly, this is a process since it's in a circle, and this is a resource since it's in a square, right? So always whenever we are going to denote a resource, we are going to use a square like this, and whenever we want to denote a process, we are going to draw process in the form of a circle like this. Okay, so what does this mean? Let's talk about this figure right now. Resource R is assigned to process A. Now this arrow is extremely important over here. So we know that this is a resource because it's a square, and this is a circle because this is a process since it's drawn in the form of a circle, right? If an arrow is drawn from a resource to a process, it means that this resource has been allocated to process A, to whatever process over here is. So if a circle is coming from a resource and going towards process, it means that that resource has been allotted to process A. So this printer, for example, has been given to process A, right? So this is one of the denotion. This is how we denote this thing. Similarly, for process B, it is blocked and is waiting for resource S. So forget about block for now. This diagram, if we talk about this diagram, if you see the arrow is going from circle, from process to resource, which is opposite to this. Over here, the arrow was going from the resource to the process, but over here it's opposite. The arrow is going from a process to the resource, which means that B is looking for, or B is waiting for resource S. All right, B is waiting for, or B is looking for resource S. Over here, resource has been allocated to process A. Now let's see what's going on over here. So this is a resource, this is a process, this is a resource, this is a process, right? So let's see what this diagram means. Let's decode this. What this diagram tells us that, let's start from here. So it's a process, we know it's in a circle, so it's a process. So process is looking for resource T as per this diagram, right? The arrow is going from the process to the resource, same way, which means that this process C is looking for or waiting for resource T, right? And this is what is written over here. Process C is waiting for resource T or looking for resource T to be allocated. And if we see this diagram, if we see this square, arrow is going from this square to this process, right? Which means that this resource has been allocated to process T. So resource T is assigned or allocated to process D, right? And if you see from here, the process D is looking for or waiting for resource U. Process D is waiting for resource U because arrow is going from process to the resource. Similarly, resource D has been allocated to process C. So resource C is assigned to process C. Now what is happening is C is waiting for T, but T is already assigned to D. D is waiting for U. U is already assigned to C. Let's maybe make it little simpler. Let's call this a printer. Let's call this a scanner, right? So process C is waiting for printer to get free so that process C can use that printer. Right now this printer is being used by process D, right? Like this. Now process D wants to use a scanner, but scanner is assigned to process C. So currently process C is using the scanner, but process D is looking for that scanner. Now they are in a deadlock. Process C and D are in a deadlock. They both cannot complete their execution. Who will complete first? We don't know, right? We don't know. So who will release the resource first? We don't know. Right now, even for 1 millisecond or 1 nanosecond, they are in this situation. We will say they are in a deadlock, or there is a possibility that they might end up in a deadlock, right? Now both of them, process C and process D, cannot complete their execution because the resource they are looking for is assigned to another process, right? Same is happening here, same is happening here. I hope this is much clearer than the previous slide now. So a concept in which a process is looking for a resource that is being assigned to another process, and that other process is looking for a resource that is assigned to another process, is said to be in deadlock. Both of these processes are said to be in deadlock. They cannot complete their execution and they might stay like this forever. You never know, right? So this is the concept of a deadlock. Let's talk a little bit more about deadlock. How can a deadlock occur, right? If we know how they occur, we can fix them, right? So there are 4 conditions for deadlock to occur. Now these 4 conditions have to, in order for a deadlock to occur, these 4 conditions should hold simultaneously, right? We know about mutual exclusion. First of the conditions is mutual exclusion, which means that only one process can run at a time for a resource, right? So only one process can use a resource at one time. So if process 1 is using CPU, no other process can use CPU, right? So P1 is using CPU, P2 cannot use CPU. We know that, right? Because only one process can use a processor. Same applies to any other resource, memory or so on, right? We will call this mutual exclusion, and this is what we have been doing. This is what we have done in our programs as well. This is the first condition. The second condition is hold and wait, which means that if a process is holding one resource and it is waiting for an additional resource, then this condition is said to be a hold and wait, just like what we had over here in our previous slide. So hold and wait for C means it is holding one resource and it is waiting for another resource, which means that this process is in condition hold and wait. It is holding one of the resource and it is waiting for another resource. So this condition is called a hold and wait condition, right? The other one is non-preemption. A resource can be released only voluntarily by the process holding it after that process has completed the task. Now preemption, we already know what a preemption is. Preemption means, let's maybe use this diagram again. So let's assume P1 is using CPU, P2 comes, which is maybe of high priority or whatever, so CPU can be given to P2 and P1 will wait, right? This process of giving CPU, taking or snatching CPU from process 1 and giving it to process 2 is called preemption. We discussed that in the previous lecture as well. Now in deadlock categorization there is no preemption, which means that the process will leave the resource only after its completion. So if process 1 is using CPU, you cannot snatch CPU from process 1. Your process 1 will leave CPU only when it's complete, when it's done using CPU. You cannot, operating system cannot snatch or take CPU from process 1 before its completion. So this is the third condition, which is non-preemption. Then there is a circular wait, which I already told you over here. This is a circular wait, so process is waiting and the other process is taking that, other process is looking for another resource which is being allocated to C. Now this is what I mean by circular wait over here. So these four conditions need to hold true for a deadlock to occur simultaneously, and we know all of them. We have talked about them. At least three of them we already know. Fourth one we just discussed right over here. So these are the four conditions that can make a deadlock occur, right? So we need to fix some of these conditions to avoid a deadlock, right? So let's see how can we do that. Now how to handle a deadlock? Now there are many ways of handling a deadlock. So in order for a system to never get a deadlock, which is the first condition, first method of handling a deadlock is to prevent a deadlock. The second condition is to avoid a deadlock. So we need to first prevent the deadlock. I mean, this is one of the methods of handling a deadlock. The second condition is, or second method is, to avoid a deadlock. We'll talk about both of them in detail in a while. The other method is let deadlock occur and then we will fix it, right? This is another way of handling deadlocks. So the system will allow deadlock to happen and then we will recover from it, or we will fix that deadlock. So this is another method. Over here we will not even allow deadlock to occur, but over here we will allow deadlock to occur, but then we will recover from that, or we will fix that deadlock, right? Okay. The third major method is to ignore the deadlock and assume that it had never occurred. And most of the modern operating system, they use this. This is called an ostrich method, and we'll talk about that at the end of this lecture. So deadlock normally doesn't occur too much in operating systems. That's why most of the modern operating system, they don't care about deadlocks, right? They don't occur too much. I mean, few of the conditions, they might occur randomly, they might occur quite often, so they need to be fixed. But there are some of the conditions that are related to memory and so on that occur maybe once in 5 years or 6 years. So developers do not spend a lot of time fixing that. Instead, they will just ignore deadlock. So if deadlock occurs, what you can do is you can go to, if you're using Windows, you can go to task manager and just close that process or close that. This sometimes happens, right? So your system freezes or your program freezes, and what you do is you either wait for it or you go to task manager and close it from there, right? So this is how modern operating systems, most of the modern operating systems using the distribution or Linux, they are handling it like this. But there are other ways that need to be fixed, that need to be used to fix deadlock, right? All right, so let's start with deadlock prevention. All right, deadlock prevention, as we discussed, that we need to take care of mutual exclusion. Mutual exclusion, as we said, that it means that a process can use, let's talk about one resource, which is CPU. So a process can use a CPU, but other processes cannot use that, right? So mutual exclusion is not required for shareable resources, right? But hold for non-shareable resources, right? So mutual exclusion means that, as I told you, that one process cannot use a CPU if another process is using the CPU already, right? Similarly, if a file is being read or being written by, let's talk about a reader writer, since we talked about reader writer. If a process is writing a file, then another process should not read that file, right? Similarly, in databases, if some process is writing to database or updating the databases, other processes should not work on that, should not read it, should not write it, right? So mutual exclusion is one way of fixing this problem, and mutual exclusion is true for it's not required for shareable resources. If it's if we go back to our same example, CPU, process 1 is using CPU, process 2 is looking for CPU, it wants to use that, then mutual exclusion means that until P1 is done, it cannot be given to P2, right? It cannot be given to P2, or we can preempt, yes, but right now since P1 is using it, P2 cannot use it, right? So this is a shareable resource. CPU is a shareable resource. So mutual exclusion is not required in the shareable resources, because we know that since this process is using it, other process cannot use it, right? If there is a non-shareable resource, then mutual exclusion is definitely required, right? Mutual exclusion is required. For example, if process 1 is always going to use CPU, then other processes are not going to look for CPU even, right? So this is mutual exclusion for prevention of deadlock. The other one is hold and wait. Now there must be a guarantee that whenever a process is looking for a resource, it does not hold any other process. So let me give you an example. So if process 1 is using a scanner, and let me just use a diagram like what we did previously. So resource S, scanner, is allocated to or assigned to process P1, and it is looking for a resource printer, right? It is looking for a resource printer. So this is how we draw for our deadlocks. So it's not a deadlock, but this is how you draw a diagram for the deadlocks. Okay, so what hold and wait means is, since process 1 is using a scanner and is looking for a printer, we have to make sure that P1 will only execute when no other process is using printer. So for example, if we had another process P2 and this resource is assigned to P2, then we will not give any of these resources to any of these processes. This is what it says over here. Now hold and wait must guarantee that whenever a process requests a resource, so P1 is requesting for P printer, it does not hold any other resources. So in order to prevent a deadlock, we have to make sure that if a process is looking for another resource, it should not already have another resource, right? It should not have any other resource already. It should not be holding it, because P2 might be looking for this and we end up in a deadlock. So in order to prevent a deadlock, we have to make sure that whenever a process is looking for something, those resources should be available for it. So for example, if P2 is not there, and nobody is using this printer, then it's absolutely fine. Process 1 is using a resource and it can always go for printer, no problem, because no other process is using this one. This is what we are saying. But if this is being used by another process, then process 1 has to leave this scanner as well, right? It has to leave this scanner as well, and you will see that how we can do that. So if process 1 is looking for a printer which is being used by process 2 and P1 is using a scanner, then P1 will not ask for this printer unless and until it will let go the scanner as well. So it will let go the scanner, and basically what is happening is, for P1 a resource queue is generated, which means that it will have a scanner. P1 is looking for two resources right now in this example, which is a scanner and a printer. So a queue will be maintained for process 1, which will contain all the required resources for P1. So scanner and printer, when both of them are available, they will be given or assigned to P1. Otherwise, they will not be, one of them will not be given. If all of these are available, only then they will be given to P1. Of course, they will have other challenges then. There are some consequences of doing that, but we will discuss about that. And one of those consequences is starvation. Then P1 will keep on waiting. It will be starved for resources. It will keep on waiting for resources unless and until both of them are available, or maybe it's looking for 5 of them. Now P1 might wait forever since it's looking for resources and cannot get any one of them because they are being used by different processes, right? So P1 or any other process can get resources only when all of them are available. This will definitely avoid the deadlock, right? Because all of them are available and we can give it to P1 and nobody else will look for them. And similarly, if P2 is looking for resources, multiple resources, a queue will be maintained for P2 as well. So it might be looking for camera, it might be looking for keyboard, right? And when all of them are available, only then it will be given to P2. This way, we solve the deadlock problem. We can prevent the deadlock. But then there is another problem that can occur, which is a starvation problem, that in this case P1 will keep on waiting for resources, and this wait might be for hours. Some resources might not be available for forever, for a long time, right? So that's another problem that we can solve by another way, but right now, at least by doing this, we can prevent the deadlock, right? Now, as we talked about over here, these 4 techniques to prevent the deadlock, we have talked about 2 of them. So using those, we can prevent the deadlock, right? We can prevent the deadlock. As I talked about over here, if mutual exclusion is done for non-shareable resources, so for example, this scanner is not being shared by any other resource, then P1 can always look for another resource because nobody is going to use a scanner. Scanner is always used by process 1, so it doesn't matter, right? And for hold and wait, if it's looking for resources, we have to make sure that all the resources are available. Only then process 1 will ask, only then those resources will be assigned to process 1, right? Next is no preemption. Preemption, as I said, it means that something will be taken from one of the process and be given to somebody else. So the other condition when we are talking about deadlock prevention, in order to prevent the deadlock, is to not preempt, right? If a process that is holding some resource requests for another resource that cannot be immediately allocated, then all resources currently being held are released, right? Now, as I said over here, this is actually the progression to the next condition over here, which means that if process 1, again going back to the same example, if process 1 is using a scanner and it needs a printer, but printer is being used by process 2, then even this scanner has to be taken away from process 1, so that if somebody else is looking for this scanner, at least they can use a scanner, right? Because if P1 keeps on holding this and waiting for this one, then any process which is looking for a scanner might keep on waiting for scanner as well. So non-preemption means you have to let go the other resources, right? Because we cannot preempt. We cannot just take this scanner and give it to somebody else. We have to put a condition first that if process is looking for some other resources and it is holding one of them, then it has to let go that resource also, so that other processes can at least can use that, right? And then there is a circular wait, which means that total ordering of the resources are important. So which means that there might not be only one scanner, there can be multiple scanners, as we're gonna see in coming examples and coming slides. These resources might have different instances, so there might be 5 different scanners, there might be 5 different printers, then they can be used as separate resources, so they can be given, right? So the increment of resources is very important, and that increment should be used by operating system wisely, and you will see what this means in coming slides when we are going to prevent a deadlock using an example. Let's now talk about avoidance of deadlock. Now, deadlocks can be avoided. How they can be avoided? Because there is a very less chance that all the resources are being asked by different processes at the same time. So process 1 is looking for scanner at the same time, process 1 is looking for printer at the same time, and same P2 is also looking for the scanner at the same time, P2 is looking for printer at the same time. It doesn't happen very often, but it can happen. So the avoidance is we can avoid that. So system, so how to avoid that? I mean, it's very rare, but it can still happen. How to avoid that? That operating system needs to know the demand of each process and number of resources it has, right? So operating system should know that in the code of process 1, how many time it's looking for the scanner, how many time it's looking for the printer. Similarly for process 2, how many time it's looking for the scanner, how many times it's looking for the printer. So operating system should know that. So each process should tell this information to the operating system, that I'm looking for some resources, and these are my resources, and I'm going to look for them that many times. All right. So operating system should know that. Besides this, operating system should know, obviously, how many scanners are there attached to it, how many printers are there attached to it, how many cameras are attached to it, and so on, right? This will give a lot of information to the operating system, and with this information, operating system can work with some algorithms to avoid the deadlocks, right? To avoid the deadlocks. So if this information is provided to operating system in advance, then operating system can work with some algorithms, some techniques that can actually avoid the deadlocks, and you will see how we can do that. Let's talk about safe and unsafe states now. A safe state is a state where all the resources are being utilized by all the processes wisely, and none of them they end up not completing their execution, right? That is called a safe state, and let's look at that with an example. Let's assume we have a system like this, A, where what is happening is these are our resources. So these are these are our processes, A1, process A, process B, and process C, and these are few resources. These are few resources. It can be printer, it can be whatever, but there is only, so we are talking about only one resource right now, right? So there are 3 printers, 3 times maybe printer is required by A, 2 times printer is being required by B, and 2 times printer is required by C. So something like that. All right. So what I'm going to do is I'm not going to talk about resource printers and scanner. Let me call it a resource. These are just resources. It can be any resource, right? Just to avoid some complications. So process A right now has 3 resources. Process B right now has 2 resources, and process C has 2 resources. In order for process A to complete its execution, it needs total of 9 resources, right? Right now it has 3. It needs 6 more resources to complete its execution. 9 minus 3, which is 6, right? So A is looking for total of 9 resources to complete its execution. However, right now it has 3 of them, so it needs 6 more. All right. So similarly for B has right now 2 resources. So 2 resources are being assigned to B, and it needs total of 4 resources to complete its execution. So it's looking for 2 more resources, right? Similarly for C has 2 currently, and maximum it needs is 7. It needs 5 more resources to complete its execution. So this is the scenario, and currently free resources we have available are 3. So we have only 3 resources available right now that can be given to any of these processes at one time. So 3 resources cannot be given to them at the same time. So 3 can be given to A, but then B and C have to wait because all 3 are consumed, right? So only at a time one process can use these 3 resources, right? All right. So let's see how we can work this problem out. So if I give these 3 resources to process A, will it be able to execute? No, because 3 plus this 3 will be 6. It requires 9 of them. So even if I give 3 of these resources to A, it would still not be able to complete its execution. That's a problem, right? Let's see what happens next. So let's check B. If I give 3 of these resources to process B, can it complete its execution? Yes. So I don't have to give all 3 of them. I can give 2 of these 3 and it can still complete its execution. Great. Let's check C as well. So it has 2 resources. It needs 7 to complete. So it needs 5 extra resources to complete. But we don't have 5, we have only 3. If I give these 3 resources to C, it won't still be able to complete its execution. Alright, so we know that. So how about we give 2 of these resources to B so that at least B can complete, right? So we give 2 of these 3 resources to B, and that's how we come here. So now we have this situation, right? So we have given out of 3 resources, we have given 2 resources to B. So B now has 4, it needed 4, so it can complete. So B has completed its execution, right? B is done, right? When B is done, which means that these 4 resources are now free, right? Since B doesn't need them anymore, B has completed its execution. So process B is no more there, right? So these resources are now free. So we will give those resources back to our operating system, telling them these are free resources. Free resources. We already had one free resource, 1 in this one, and now in this round we have 4 more resources given as free because B has completed. So we can give the resources used and completed by B to the free queue. Now we have 5 free resources, 1 from previous round and 4 by taking it from B since B is complete. Now let's do the same thing again. What if I give 5 of these to A? Can A complete? No. 3 plus 5 is 8, it needs 9, so it cannot complete. So we cannot give these 5 to this A, right? How about we give these 5 to C? If we give these 5 to C, it can complete. Yes, that's correct. So how about we give it to, we don't have any more processes, so how about we give these 5 resources to C so that it can complete its execution. So we go here and this is what we have. So we have given those 5 free resources, all of them, to process C, and it has completed its execution. Our free resources are 0 now, right? So since C is completed now, let's go to the next round, which means that we can give all these free resources to the operating system back, telling them that these are free resources. So we have 7 free resources and we have only one process left. B and C are completed. Can we give these 7 resources to A and it can complete? Yes. So let's give 6 of these 7 resources to A so that it can complete its execution. So after doing that, A can also complete. So all of these 3 processes, if we move like this, if we give resources to C first, if we give resources to B first, then we give resources to C, then we give resources to A, we can say that all of these processes, if we follow this pattern, then they can complete this execution. If something like this can happen, then we call it a safe state, which means that using our resources wisely, we can make all the processes complete their execution. And this is called a safe state, where all the processes, given the certain amount of resources we have, all the processes can complete their execution. This is called a safe state, right? I hope you understand this. Let's talk about unsafe state now. Let's talk about unsafe state now. And what is an unsafe state? Contrary to safe state, means that given the sources, given the resources we have, the processes, whatever way we use our resources, the processes won't be able to complete execution, right? Let's see how it works. So we have same scenario, I think so. Yeah, whatever. I mean, we have this scenario now. So again, A has 3, it needs 9 to complete. B has 2, needs 4 to complete. C needs 7 to complete, it has 2, right? And free resources we have is 3, right? Okay. So let's give out of these 3 free resources, one of the resource to process A. Intentionally we are going to make an unsafe state, just to make you guys understand. All right. So if I give out of 3 one resource to process A, will it complete its execution? No, it will not complete its execution, which means that we have now 2 free resources, and now we move next. Since A has not completed its execution, we have given it to A. Operating system maybe made a mistake or whatever. Operating system has given this to A, and we are left with 2 free resources, and we have given these 2 resources to B now. So B can still complete its execution, right? Which means that after B is completed, our free resources are 4, right? All of these resources have been released by B. We can use them as a free resources in the free resource queue, right? Now we are left with 4. If I give these 4 resources to A, can it complete? No, it needs 5 of them to complete. If I give these free resources to C, can it complete? No, it needs 5 resources to complete, which means that if we use a sequence like this, A, B, and we are left with, I mean, whatever we give now, either we give it to A or C, this end up in an unsafe state, which means that processes were not able to complete their execution. So this kind of state is called an unsafe state. So operating system has to make sure that resources are given in such a way that all processes complete their execution, right? And if we do that, we can avoid our deadlock, right? I hope you guys understand this. This is an exercise which I would like you guys to do it. I'll do the first one for you, and rest of the two you guys try it, all right? And you just have to tell case 1 is a safe state or not, case 2 is a safe state or not, and 3 safe state or not. Let's do the first one. I'll do the first one for you, you do the others. Okay, so let's see if this is a safe state or not. So we have two free resources. X needs 2 to complete its execution, Y needs 4 to complete its execution, Z needs 6 to complete this execution. Let's give these two to X. Alright, so it will complete its execution. 2 plus 4 is 6. It will be executed. Our free resources will now be 6, right, because they have been released by X. Okay, if I give this 6 to Y, will it complete its execution? Yes. If I give this to Z, will it complete its execution? Yes, right? So I can give it to anybody. Since this is a straightforward calculation, let me give this to Z. So if I give this to Z, it will complete this execution, and I will end up having 10 free resources now. And out of these 10, I will give 4 to Y, and it will complete this execution as well. And I will be still left with some resources, which means that this is a safe state if I do X, Z, and Y, right? So with the same amount of resources, if I allocate them, if this pattern is used differently, I might end up having an unsafe state. So our exercise over here is to find if there is a safe state or not, right? If there is a safe state, or if there is a safe state somehow, which we just found, it means that this case 1 is safe state. If we cannot find any safe state, then it means that it's an unsafe state. So you guys try the other two cases yourself. So this is what safe and unsafe state is. I hope you guys understand what a deadlock is. I hope you guys understand how to draw them, because in final exam I might ask you guys to draw something for me using these deadlocks, and I'm gonna draw a couple of others which are coming in coming slides, and I'm gonna do that for you as well, so you guys can further see how we can work out with deadlocks. But before going there, I'm going to talk about Banker's algorithm, and we are going to implement this Banker's algorithm in our lab exercise as well today. So let's talk about this, and we will get back to this when we are doing our lab exercise. So we will get back to this again, but let's see what a Banker algorithm is. Banker algorithm is used by operating systems to make sure that resources are assigned wisely to find a safe or unsafe state, in simple words, right? Banker algorithm is used by operating system to see what is a safe state and what is a safe state pattern and what is an unsafe state pattern, right? And we have to make sure that there is a safe state. Operating system has to make sure that it has to find a safe pattern, safe state pattern, and it uses this algorithm, Banker's algorithm. So in Banker algorithm, we have multiple resources. We have seen this. There are multiple resources, right? And these multiple resources can be of different types, and we will see that in our exercise as well, and we will see that in coming slides as well. So there are multiple resources, we know that. Each process must provide its information of how many resources it needs, how many resources it has, right? And this is what is happening over here. So process X already told operating system that I have 4 of them and I need total of 6, right? So this is the information that Banker algorithm requires. So it needs multiple instances of resources. Each process should tell how much it has, how many resources it has, and how many resources it needs for its execution. Then Banker algorithms do understand that, and this is what is kept in mind, that some processes might need to wait, right? As we discussed previously, that if one process is looking for 2 resources and it is holding 1 resource, then it might has to release that resource as well, and operating system will get back to the process with all the resources later on. So a process might need to wait for some time. Banker algorithm is all about that. When a process gets all the resources, it needs to return those resources. It needs to release those resources. So a process cannot keep the resources forever, obviously. It needs to return those resources back to the operating system so that other processes can work on those resources. So this is what banker algorithm is all about. And banker algorithm uses this type of data structure. So there will be a vector or a matrix, I'll say a vector array in programming language. So we'll be having an array of available resources, we'll be having an array of maximum resources, we'll be having an array of allocation, and we'll be having a need array. Over here we are having a matrix, but I'm calling it array because ultimately matrices will be converted into arrays, right? So these are the data structures which are going to be used in banker's algorithm. I'm gonna go through this very quickly because I'm gonna explain this in a lot more detail when I'm writing the code for you, right? And we are going to see through each line what each line is doing as always, so that you guys further understand what this actually means. But this is actually telling operating system that I have these many resources, I'm looking for these many resources to complete, and these are currently allotted to me, and so on, right? And these are just data structures just to tell that how these are maintained. So these are basically maintained in vectors. I'm going to call them arrays. So these are going to be maintained in an array, right? Okay. And this is a safety algorithm. Safety algorithm means that we need to make sure that your algorithm, because we are avoiding it, right? We have to make sure that it's safe to give, because we are checking the safe state, right? And how to check that safe state, we are going to use this safety algorithm. I'm not going to go into the detail of this algorithm because this is a traditional algorithm used in textbooks. I'm going to tell you an easy way of doing it. This is how I do it when I program it, and I'm going to program it with you guys so that you guys actually understand what's going on. So you are free to go by this one as well. This is the textbook algorithm, or the one which I think is much simpler than this one. You can use that one as well. So I'm going to explain that when I'm programming, right? So I'm going to go there, and for request and resource, again I'm going to use an algorithm which I believe is much more easier than this part of the algorithm. So, and it's pretty simple, to be honest. I mean, look at this, for example. I mean, available resources means how many are available, currently available minus the requested one, right? So we minus from them. And if you look at need means how many it needs currently and how many have been already allocated to the process. So these are simple maths, and we're going to do that in programming. So I'm not going to spend too much time over here. I'm going to spend reasonable time when I'm going to program it. So we'll talk about that over there. So this is this, and this is an exercise which I believe I'll do it for you. So let's do this exercise together to see what is the pattern to have a safe or unsafe state, right? Will this end up in a safe state or a unsafe state? If you see over here, we have two resources, right? So R1 and R2, right? And they have multiple instances. For example, this is a printer and this is a scanner. So there are so process X has one printer already, and it's looking for 8 more printers. I mean, sometimes it's not very reasonable. That's why we keep on calling them resources, R1 and R2. But in real example, obviously you can talk about memory addresses, amount of memory over, then it will start making sense to you. But just to make it simpler for you, these are just, I mean, resources. It can be any resources, and these are the instances of those resources. So printer, there is one printer and looking for 8 in total. So just like that. So let's talk about, let's call them resources R1 and R2. So what is happening over here is process X will complete its execution if it has total of 8 resources R1, and it will complete its execution when it has total of 9 R2. So it needs both of them at the same time. If you remember, we said that a process should be given all the resources if all the resources are available. Only then the resources are given to the process. Otherwise, process has to wait, right? So this is what we said last time. So if you remember, so process 1 is looking for them. So if process 1 doesn't have all of R1, which is 8, let me call this 8, and R2, total of them are 9. So if process 1 doesn't have all of them, it will not be given to process 1. It will be given to process 1 when it has maximum of these available. For example, if you see currently available are 4 and 4. R1 are 4. 4 R1 instances are available or 4 R2 instances are available, right? So if we give 4 over here to X, it will not complete. If we give 4 here to R2, it will not complete, right? So what should we do to make it complete? Let's talk about that. So let's see over here. So we talk about this again. So there are 4 available for R1, 4 available for R2, and let's see how it can work out. So we already talked about X, that it's not going to work out. So Y, if we give 4 to Y, it will complete. R1 will at least complete. We give 4 to R2 for X, for Y, it will not complete because it needs 6 of them and we have only 4 right now. Let's talk about Z. So if we give 4 to Z, 4 R1 resources to Z, it will complete. And if we give 4, it needs only 1 over here. If out of 4 we give 1 to 1 R2 resource to X, it will complete. So we can run at least Z. So this is what is happening over here. So we have given out of 4 all of 4 resources to all of R1 resources to X, which is happening over here. So we have given 4 of them over here, and out of 4 we have given 1 over here. So at least Z is complete. Z is complete. Once Z is complete, all these 6 resources are now free. All R1 has now 6 instances free, and R2 has 6 instances, 3 from this and 3 previously it had, right? So now we have 6 and 6 available. What about we give R1 6 instances of R1 to X? Will it complete? No, it needs 7. R2, no, it needs 7 again, right? So what about Y? If we give R1's 6 instances to Y, will it complete? Yes, we can only give 4 and it will still complete. We give 6 of R2 to Y, it will complete. Yes, so let's do that. So out of these 6 we give 4 to Y, and R1 resources will be enough for completion. Similarly for this we give all of the 6 and it will complete for R2. So now we are left with R1 2 and R2 0, but then Y is done, so we can bring all these free resources back, and we have this situation now. So we have available 8 now and 9 because Y has released all the resources now. If I give 8 over here, it will complete. Yes. If I give 9 over here, it will complete. Yes. So but we don't have to give all of them because this is not the requirement. So out of these 8, I will give 7 R1 to X and it will complete its execution. I will give out of 9 R2 instances to R2 X process and it will complete as well, and we are done. After that our free resources will be this. So the save sequence will be, we start with Z process, then we give it to Y process, then we give it to X process, and this is using Banker's algorithm, and this is what you're gonna see what we are going to implement in our lab exercise. So this is the save sequence we found, right? So it means that if we go by this sequence, this system is going to give us a safe state. We normally call it a safe state or a safe sequence, whatever you want to call it, right? So this was the exercise. Now we have talked about the first method of handling deadlocks, which was this one. It contained 2 things, prevention and avoidance. So we have done both of them. Let's talk about now second method, which is to detect the deadlock, let deadlock occur, and then we'll solve it, right? So this is the technique we're going to talk about now. So this is called deadlock detection and recovery. So we will let deadlock happen, we will detect it, and then we will recover from it, or we'll fix it, right? This technique, deadlocks are not prevented, they are not avoided, they are allowed to occur, and then we just fix it. There's a simple way, right? And how to do that? How to do that? So first thing is to detect a deadlock, right? So we are going to talk about detection of deadlock using one resource. I'm not going to talk about multiple resources R1 and R2. So we are going to talk about one resource of each type, or for example we are going to have one instance of each resource. So for example, in previous example, if you see, we had multiple instances. So for example, with printer we had multiple instances, 8, 6 and so on, right? Over here we are going to talk about multiple resources, but only one instance per resource, right? You will see now. Okay, so in this technique what we will do is we will use only one resource of each type. So there will be not multiple instances, but one instance for each resource. System will have one printer, one scanner, one camera, one keyboard and so on. if a resource has a cycle in it, it means it has a deadlock. I will explain to you what a cycle is, and that part of deadlock will have all the processes in it that will be deadlocked. I will explain that to you in a while also. If there is no cycle, then there is no deadlock. Let's do that with an example. All right. So what's happening over here is, let me draw this for you and let's see what happens. So let's draw this. So process A holds R and wants S. All right. So we have process A. It holds R. So it holds R. So R is assigned to A and it's looking for S. So process A is looking for S. So it's looking for S. So we are done with the first one. So process A holds R and it wants S, right? Okay. So process B holds nothing but wants T. So we have another process which is process B. It holds nothing but it's looking for T. So it's looking for process T. So this is our process T, and process B is looking for, wants to get process resource T, right? This is how we do it. Okay, process C holds nothing but wants S. So we have process C. It holds nothing but it's looking for S, like this, right? Just like A. So process C holds nothing but wants S, like this. Process D holds U and wants S and T. Wow. Okay, I have to draw it somewhere, maybe where I can just, okay, so let's draw it here. Maybe process D holds U. So we have a U here. So process U. So it holds U. Process D holds U and wants S and T. So process D is looking for T as well, and it's looking for S as well, like this. Okay, S and T. Yeah. Process E holds T and wants V. So process E holds T. It holds T, which means that it's resource T is assigned to E. So process E holds T and wants V. So and it's looking for V. So it's looking for V, right? And this is also done. Process F holds W and wants S. Okay, process F is holds W. So process F holds W. Let's do W. Process F holds W. It holds W and wants S, and it's looking for S. Everybody is looking for S. Okay. And process G holds V and wants U. Where is, okay, we can draw it here safe. So process G holds V. Process G holds V. Oops, this is a resource. Okay, it's a resource. Okay, so process G holds V. So process G holds V and wants U, and it's looking for U. Let's see if we have a cycle over here. Do you see a cycle over here? I clearly see a cycle over here. If you see, what I want to do is I want to try and change the color for this. You can see there is a cycle, clear loop happening over here, clear loop. So if you start from D, it's like a cycle, right? It's a cycle happening over here. It's a cycle happening over here, which means that if there is a cycle in your graph like this, it means that D, E and G, these are the three processes involved in this cycle. They are all deadlocked. They are all deadlocked, right? So by drawing this, we can detect if there is a deadlock or not. You can clearly see that there is, D is looking for T, T is being held by E, right? E is looking for V and V is held by G, G is looking for U, U is held by D, right? So this is a cycle, which means that D, E and G are deadlocked. They are in a deadlock. They are in a deadlock situation and we need to fix it. So since we are talking about deadlock detection and recovery, we have already detected the deadlock. We need to just fix it. We need to recover from this deadlock. So this is how you can detect a deadlock. By drawing something like this, you can detect if there is a deadlock or not. Very simple. and this is what we said. So this is a deadlock, like we said, D, E and G, right? So D, E and G, and there is no other deadlock, by the way. There doesn't seem to be any other deadlock. There can be multiple deadlocks, but right now there is only a single deadlock. There is a single cycle, and it means that these are in a deadlock, and this is how they look like, the deadlock. Now you do this exercise yourself. I'll leave it to you guys. I have done one for you, like this is what I have drawn for you. You can draw this yourself. I want to give you more and more exercises. You can try some exercises creating yourself. It's just giving some processes a name and asking them to hold a resource and looking for something else. So try to do it yourself so that it gives you more practice, because since I said that I might bring a question in final exam from this, so please make sure that you do enough exercises so that you understand how this concept works. And it's all about drawing, it's not programming, so I hope it's fun. So try to do this yourself. Now fine, we know the way to detect a deadlock. How do we recover from it? How do we fix it, right? Okay, so there are multiple ways of doing that, but first of all, let's talk about preemptive resources and non-preemptive resources before we go to recovery of deadlock. So what is a preemptive resource? So preemptive resource is a resource that can be taken away from a process. So process 1 is using a scanner, and process 2 came, and process 2 is looking for this scanner. It can be taken from process, so scanner can be taken from process 1 and can be given to process 2, right? This is called preemptive resources, right? Memory, for example, right? Memory can be given to another process if it has a high priority. CPU can be given to another process if it has a high priority. So these are called preemptive resources. Now there are some non-preemptive resources also, which means that if P1 is working with scanner, it cannot be given to process 2 if scanner is a non-preemptive resource. Like for example, CD burning is a great example of non-preemptive resources. If you are burning a CD and you take CD-ROM away from the process that is burning CD, then you might spoil the CD burning process. The whole CD might go wasted. And I'm sure you guys have used CDs, and we all use CDs. I'm old enough to have used floppy disk as well. So you might have used CDs. So CD burning is a good example of non-preemptive resource, because if you take the CD-ROM from that process that is burning a CD, the CD will be spoiled, right? So these are called preemptive and non-preemptive resources. Okay, so how to recover from a deadlock? We have detected a deadlock. How to recover from it? Recovery through preemption. Now that's why we detected that's why we discussed preemptive resources and non-preemptive resources. So we can recover using preemption. In this technique, what we can do is we can take a resource from one of the processes and give it to somebody else, so that we are not stuck in a deadlock, right? So for example, if I go back here, let's talk about process E. Process E has T, so process E already has this resource, and it's looking for resource V, which is being taken by G. So they are stuck in a deadlock. Now how to fix this deadlock? What we can do is we'll take this process V from G and give it to process E. Now process E has both T and V. It can complete its execution, and once it's done, we can give this process back to this resource back to process G. So we can take resources from one of the processes and give it to another process, so that at least that process can complete its execution. So this is called preemption. This is how we can recover from deadlocks using preemptions. But this is very, very difficult to do, because you have to then keep on checking which process has which resource, right? You have to keep on, because and the whole process is very, very fast, especially when you are talking about scanning or keyboards and so on. The process is too quick that you have to do whole calculation of taking the process and giving it to somebody very quickly, and that's very difficult to do because of the speed, right? It's very difficult to do that. So, and also it's very difficult to do that because of knowing what resource which process has. You have to take care of, at each time interval, you have to make sure that you know which resource is being kept by which process and which resource is required by another process. It's very difficult to keep track of that. So that's why preemption becomes a little bit difficult, but there is a way of doing that, of course. The other way is a rollback. Rollback means we do so what we do is, for example, let's go back to the same example. Let's assume that this is, let me draw it better. Okay, so process 1 is looking for a scanner. So process 1 is looking for a scanner and it's holding, for example, a keyboard, right? So it's holding a keyboard. And process 2 comes, so right now at this stage, process 1, so let's call it time interval t1, right? This is time interval t1. At time interval t1 there is no deadlock, right? There is no deadlock. So process 1 can look for k, for resource k, it can use it and release it later. But what about, let's talk about another instance. So after 1 nanosecond or 1 millisecond, what happens is, before p1 can actually get k, p2 got k, right? So p2 got k and p2 is also looking for s. Now they are stuck in a deadlock, right? Now they are stuck in a deadlock. So in order to solve this problem, what we can do is we use a rollback. So maybe this is time interval 2. So what we do is, before the deadlock actually occurred, we go to that time interval time. We go to a time interval where there was no deadlock. So we roll back to that interval. It's just the same example. Like, for example, you are working on a Word document, and that Word document, or let's take an example of a game, for example. So you are playing a game, I don't know, whatever. I am playing Age of Empires these days. I mean, an old game which I used to play several years ago, Age of Empire 3. I don't know why, but I started playing again during the weekends, only for 1 hour maybe. So for example, you are playing a game and you have created a checkpoint, or you have saved your game, right? So you have saved a game because that mission is very difficult, and you move on, and unfortunately your player got killed, right? So what you're going to do is, either you start your mission from beginning, or you go back and load your saved game, right, from the checkpoint you made. So normally we do that. We go back and load our game, load our saved game from the checkpoint. So you have to start from the checkpoint, right? So this is exactly what is happening over here. So we just roll back to a time interval where there was no deadlock, and this will help us in, or maybe next time when P2 comes, P1 might take this k resource before P1, before P2. You never know, right? Because P2 might be stuck somewhere else, right? So this is one way of recovering from a deadlock using the rollback. All right. Okay. Another way of doing that is killing a process. So killing a process is simple. So P1 is looking for scanner, and P1 has printer, right? So it has printer, and P2 comes, and P2 is P2 has, let's do it the right way, P2 has resource scanner and it's looking for this printer. So we are stuck in a deadlock. What if I kill P2? I'll go to task manager and just kill this process. Now P1 can take printer as well, no problem. So one of the ways of recovering from a deadlock is killing the processes. But obviously, I mean, killing the process is not the right way to do it, and sometimes it might create problems. For example, especially in databases, if a process is writing in a database, if two processes are writing in a database and one of the processes is killed, and next time the process comes, it is expecting a value, some value, and it doesn't find that value and it starts writing it. If you remember, we did a counter variable when we were talking about CPU synchronization, remember, race condition. So this killing processes can end up in a race condition. So it's not a good idea to do that, but at least we have a way to do that, right? So one way to recover from a deadlock is by killing the processes. So we can do that, right? So we are done with our second technique, which was this one. So we are done with this technique, we are done with this technique. The other one is the ignore the problem and pretend that there was no deadlock, right? Which most of the operating systems are using these days. That is called an ostrich algorithm. So this is an ostrich algorithm. So what happens is, in this algorithm or in this technique, we just ignore the deadlock. We expect that we ignore the deadlock. If there is a deadlock, we just pretend that there was no deadlock, right? And why it's called an ostrich? Some people say that ostrich, whenever it sees a problem, it's just put its neck in the ground, under the ground, and assume that there was no problem. I don't know if it's true or not, but that's why it's called an ostrich algorithm. So what we do is, in this algorithm, if there is a deadlock, we expect that there was no deadlock, and we keep on working. Why this helps and why this works? Because avoiding deadlock or preventing deadlock or detecting deadlocks and recovering from deadlock, it's a massive problem. It's not an easy, there is not an easy solution to that. So, and the deadlocks normally in modern operating system, they occur in 5 years or 10 years once. So engineers do not spend too much time finding an optimal solution for that. But obviously, I mean, deadlock is a very important concept in operating system. For example, if operating system is hanging every now and then because of deadlocks, then there is a serious problem, right? And those bugs are being fixed by the engineers, by the developers every now and then. So we don't face lagging too much of freezing of applications too much these days. So operating systems are pretty good these days handling all these solutions, all these problems. So this is called an ostrich algorithm, and very simple one. And that's pretty much it for the theoretical part. We are going to work on exercise number 1, and that is a banker's algorithm. We are going to develop a banker's algorithm, and I'm going to develop it in one way. You can develop it in any way you like, as long as it's fulfilling all the requirements. So there is not only one way of writing it, there are many ways, and if you go to internet, you will find many ways of solving this banker's algorithm. It's a very famous algorithm, and you will find many implementations of this. I use this implementation because I feel that it makes more sense to me. I'll try to help you guys understand this, and if you don't understand this, you can always get back to me, obviously. If you believe that this is a difficult way of doing it, there are many other ways that you can use. You can go to internet and see if that something makes more sense to you. You are free to use that. And as always, I'm going to program that in C language just to be consistent, since we have been using C, but you can program it in any language you want. You can use C, C++, Java, Python, whatever programming language you like. You can try it in that programming language. I don't mind. So I will see you in the other video, and I'm gonna explain you the assignment in that video as well. So up till now, bye bye. I'll see you in the other video.